Hello, my name is Anna Price, and I am a double major in mathematics and chemistry. And my senior project is using cheminformatics to predict water solubility. So first off, what is the purpose of this experiment? It is to build a model that has a better water solubility predictor with greater precision and accuracy. And you might be thinking, why is this even important? Well, all living systems require water. Every living system uses water in everyday life. So it is important to understand how the compound will behave in both terrestrial and aquatic systems. And this can also be important in pharmaceutical development for like new candidate drugs, because these compounds need to possess suitable transport properties within living systems.
Still something in
So
there.
there was an article that we based our research off of, and it was done by Charles Lowe. He had put together a water solubility data set that included a lot of compounds that had reliable water solubility data in it. And it also had some other variables that like identified the compounds. And he ran this data set through a random forest model, and he extracted the R squared and the RMSE values, which I will explain in a later slide. And the other data set that we looked at was the Jean-Claude Bradley double plus good melting point data set. And in this data set, it basically contained a multitude of compounds that had all of the melting point data for those compounds. So what is being measured? I mentioned the R squared value and the RMSE value. So what are they? The R squared value is basically the value that shows how well the data set will fit the model used. And the closer that value is to 1, the better the fit that the data set has to the model. And the RMSE value is the root mean squared error, and this shows how good the prediction quality can be of the model used. And you want this value to be close to 0 or as close to 0 as possible, because the closer to 0 it is, the better prediction quality it can have. So our target values, So also in table 1 on here that I have on the slide, it shows Charles Lowe's R squared and RMSE values. You can see that his R squared value came out to be 0.82, which shows a pretty good fit of his data set on the model. There's still room for improvement, but it's a good fit. And his RMSE value turned out to be 0.97, which shows poor prediction quality and definitely room for improvement. So our goal is to get an R squared value greater than 0.82 and an RMSE value less than 0.97. So how are we going to do that? We have a couple steps that we took to achieve this. And the first one was combining the two data sets together. So that would be taking Charles Lowe's research with his water solubility data set and combining it with the melting point data set from Jean-Claude Bradley and combining those two. The next thing that we needed to do is build a random forest model in the computer language R, because Charles Lowe also used a random forest model so that it's an equal comparison of values. And then after combining the two data sets into one, we created one sub data set, and we took that sub data set and ran it through the model that we created. And then we extracted the R squared value and the RMSE value for equal comparison to the previous research. So we had to combine the data sets. So how did we do that? So in each data set, both in the melting point and the water solubility, they both had a chemical identifier code, which was the SMILES code, which stands for Simplified Molecular Input Line Entry System. And that is basically a code that takes a compound and puts it into one string of code that is easily inputted into the computer for analysis. And this chemical identifier is not always unique, hence why we needed to convert it, because SMILES doesn't always take into account different variables of a compound, for example, stereochemistry. So we used Babel to convert the SMILES code into InChI code, which is another type of chemical identifier. And the InChI code is a lot more unique than the SMILES code because it takes into account the stereochemistry, for example. And it also definitely cuts down the probability of duplicate compounds within the data set. And I have a couple examples up here. The top one is the SMILES code. And then in the bottom, it shows the SMILES code going into the InchiKey code. And it shows that it's definitely a lot more unique. And then also a little fun fact, when we were analyzing both of the previous data sets, in Charles Lowe's data set, he actually had 2 duplicates because he only used the SMILES code. So we were able to remove those duplicates when moving on to ours. Next, we are going to move on to how we built the random forest model and why we picked the random forest model. So the random forest model is obviously the same model as the previous research, and it was picked because it handles high dimensional data modeling and it handles large data sets very well. And we obviously needed this because we were dealing with thousands of compounds at this point. We needed something to handle a lot of data points. And the random forest model uses what's called decision trees. So each of these trees come to their individual results, and then there's an averaging or a majority vote to produce the final result. So it does a lot of self-checking on itself, and it removes a lot of the error that could be popping up. For example, if there's 3 trees standing here, one says, no, this answer is true. The next one says, no, that's false. Third one can come along and be like, no, it's actually true. It self-checked itself because of that one error with the second tree. So it uses a series of true-false questions, comes to a result, averages out, and then gives the final result. And we built this in the computer program R, the computer language R. And R is typically used for like statistical computing, and it also handles large data sets well. And it's also pretty easy to use, so that's why we picked it to build our model in. And using this model, we were able to input our data set that we had created from merging the 2 data sets together, and we extracted our R-squared value and RMSE values to compare to Charles Lowe. And in the top table on this slide, you've already seen it, I've already described what's happening there. So in the bottom one is our values that we got from our sub data set. And as you can see, our R-squared value is 0.85, which is 0.03 higher than the previous research. So it's not drastic improvement, but there is a slightly better fit for our data set on our model. But then you can also see our RMSE value is 0.80, which is 0.17 lower than the previous research. So that is a significant increase in prediction quality on our model versus the previous model and data set. So then what about future work? What else can be improved on this? Well, obviously there's still a lot of room for improvement because our prediction quality is not the best, but it's significantly better. So how we could do this is refining the data set and adding more variables to it. Because as we could see that just having the water solubility data set run through the model does not give good prediction quality. But then as soon as we added the melting point data set into it, it enhanced our prediction quality. So what if we add another variable, for example, like heat of formation? The prediction quality will probably continue to improve. So that's our goal for like future researchers that get interested in this. And then that brings me to my acknowledgments. So I would like to thank ORU as a whole, but then also specifically the Department of Computing and Mathematics, as well as the Department of Biology and Chemistry for just their continued support throughout my 4 years of study here and their amazing faculty and staff. But then more specifically, Dr. Lang, who presented this project to me and helped teach me the computer science and the math behind this project. But then also Dr. Collier for teaching me why this is important. What's the important chemistry portion behind all of this? And then that will conclude my presentation. Is there any questions?
Because I don't know what she's talking about.
I know what she's talking about. One question I would ask is how many variables can you bring into it?
Yes, it was we took Charles Lowe's data set of like thousands of compounds and analyzed that. Well, he kind of analyzed it. We just kind of took it and ran with it. And then we also had the melting point data set, which again, similar concept, thousands of compounds with all of the analytics of it, combined it, created one, and then analyzed that. So yes, it was a lot of analysis behind it. Yeah. Dr. Collier, did you have a question?
Yeah.
Yes.
I know the previous person used a random forest model. Why did y'all continue to use that? Because that's not the only model used to treat the data with wild random forest model.
It was mostly because it handles the large data sets really well and it doesn't get like shaken up about it. And then also to ensure a good comparison between our values. Like, yes, it would have been nice to have a different model, but we were mostly looking for the prediction quality and not the
Watch this guy coming
the
over here.
fit. So we were looking more for the RMSE value instead of the R squared value. Both were equally important, but we were aiming more for increasing prediction than fit. And we already knew that the random forest had a pretty decent fit, so we wanted to compare the two. Dr. Desmond? Mm-hmm.
Is it all the experimental?
Oh my, this is nice.
Yeah.
Or is it based on more competitive learning? Analyze the data.
Yes.
How did that data set come about?
So we didn't gather any of like the data like for the specific compounds ourselves because there was way too many. Charles Lowe had curated the water solubility data set with like, he tested everything. He made sure that everything was accurate and up to standard. And then so did Jean-Claude Bradley with his melting point. So we just merged the two. And then the prediction quality is more of like, you have a compound that's not within the data set and you're wondering, oh, what's the water solubility of this? You can run it and then be like, oh, it will have approximately this. So that's kind of what it's used for. Yeah. Yes.
Apologies for walking late.
You're okay.
So, question is based on the you have said it in the talk today on. My question is, what is the practical value of doing all this stuff?
Okay, so that was basically saying like, obviously every living system uses water in its life. And it's really important to understand the water solubility of compounds, especially in like the pharmaceutical development. So like if someone's like, hey, I have this new candidate drug, how is it going to react? Will it transport well within the body? So that's the main application that we focused on.
I
Yes.
just want to say, I think you did a tremendous work here to combine the math and the chemistry. You took on a very significant project in doing two separate majors, but combining them together in a Winsky project. And you may have done something different on the math side. I don't totally know. But I think it's a great
Prejudice, but isn't she pretty?
Very nice. We do work
Absolutely.
in in chemistry or in any other field where you can merge the two.
Mhm.
And I think your data today was a great.
Please.
Thank you. Thank you.
How many people